Good morning, students. Today we will be discussing about Boolean algebra as minimization technique, and followed by that, we will be looking towards a new technique called Karnaugh Map or K Map. So, in the previous class, we have discussed about Boolean theorem and Boolean algebra. Okay, so we have discussed about your Boolean algebra. So, suppose I give you this particular expression to minimize, or I want you people to minimize it and implement using some logic gates. So then there are certain issues which are there, that whether whatever you do is minimized or not. So that's important. If I am doing this thing and if it is not minimized, then I might end up in a number of gates being. So if you require, suppose, x number of gates, and using minimization you will getting x minus y number of gates, then we always go for this kind of minimization technique. So that's about your Boolean algebra, that some expression is being given there and we will try to minimize that. Now question arises where expression comes from. So suppose this is a 3 variable system. We are having a system, and this system is having a list of inputs. So your inputs are A, B, C. So based on this inputs, we are having some output. Your output is Z. So we don't know anything. We are having this system A, B, C, and we are getting output at Z. Now corresponding to that, we are having a truth table like this. So your truth table is A, B, C, and output Z. Now total number of variables are 3. So how many possible combinations are there? 8 possible input combinations are there from 0 to 7. So how we are going to write it? 0, 1, 0, 1, 0, 1, and 0, 1. And this is 0, 0, 1, 1, 0, 0, 1, 1. And this can be written as 0, 0, 0, 0, and then 1, 1, 1, 1. Now output. So here you can see A bar B C. So A bar B C is nothing but 0, 1, 1, 3. So this is high. Then A B bar C bar. So 1, 0, 0. So this is your 4. Then this is your 1, 0, 1. This is 5. Then 1, 1, 0. This is 6. And 1, 1, 1. This is 7. For rest of the inputs, your system is giving output. So this is the truth table, and after truth table you will write the expression like this. So I hope you understand this. Now coming towards minimization, and why minimization is required, because we want to implement this logic using some logic gates. So this is your black box. Means we know what are inputs, we know what are outputs, but we don't know how this output is actually being coming from this particular inputs. So that's the black box. So now if we want to implement this particular function using some logic gates, then this need to be minimized. If you do not minimize, you will end up with more number of gates. But if you minimize it, you will require less number of gates. Suppose this is not being minimized right of now, as of now. So how many gates are required? 1 for A bar, then B, C. So total 2 gates. Then we assume that we are having multiple input gates. If 2 input gates are there, then number of gates required will be more. Then 1, 2, 3. Then 2, then 2, then 1. And we require 2 OR gates. If multiple input gate is available, multiple input means you are having OR gate and it is having 4 inputs. But in lab you will find out you are having OR gate with only 2 inputs. So then number of gates required will be much more. So as of now, if you assume we are having access to multiple input gates, then you are getting correspondingly 2, 3, 5, to 7, to 9, 1, 10. So you require 10 number of gates plus 2 OR gates, 13 number of gates. That is without minimization. So when you implement a system using Boolean expression without minimization, you end up with more number of logic gates, thus increasing the cost of your implementation. Also, the size of your device increases, the battery consumed will be more, and so many problems are there. So the best way is to minimize it. Now, the one way to minimize is, which we have discussed in the previous class, that is using Boolean algebra. So here you can see this becomes ABC bar plus ABC. So AB is common, C bar plus C, and this comes out to be AB. And we will be doing this entire exercise and we will end up in this particular expression. So here you can see AB is common, here AB bar is common, A bar C. So this gives you A bar C, AB bar, AB. So A is common, B bar plus B, A bar C, A bar C plus ABC. So this is the last term which we will be obtaining. So how many gates now you require? You require only,
सर ये वन स्टेप और शॉर्ट हो सकता है ना?
yeah, ये
A
देखिए,
plus BC. Yes sir.
yes, this is A plus BC. So now you require only, I'm just telling you that if you have this in between, then suppose a student thought that this is a minimized version, then how many gates are required right now as of now? A bar, BC, 2 gates, 3 gates. So total 3 gates are required. But if you work in this particular manner, only 2 gates are required. Okay, one for BC and then one OR gate. So this is how you can see that when you are going for a proper minimization, what are the benefits? Benefits are less number of logic gates, number of logic gates. So this is the first one advantage. And when you are having less number of logic gates, your cost will be less, area of your logic circuit will be less, and your power dissipation, because they are consuming the battery. So this will be less. So you will see in Boolean expression minimization technique using Boolean algebra, there is always uncertainty. We don't know that whatever we get is actually minimized one or not, or what can be done, something like that. Or if you are not sure, then you are always having some sort of doubt in your mind that yes, if it can be minimized further or not. So then people start looking forward for other alternate techniques, that if it can be minimized further or not. Then in that case, there is a need for some other technique, and that technique is called Karnaugh Map. It was invented or discovered, or the proposal was given by Karnaugh Map, and these days this particular technique is called K-map. So one more example is there. Suppose you are having this function x bar y this and this, and you want it to be implemented using minimum number of gates. Then how you are actually going for that? You will use different identities being discussed in the previous class, and you end up with this number of gates. So clearly you will find out that if you implement this, you require more number of gates, and if you implement this, you will require less number of gates. So that's the key, that we should have very good knowledge about your Boolean expression, and we should have some sort of what we can say intuition, or we can say we must be confident that whatever we done is actually a simplified version. If that is not the case, we are always having this thing that you are putting more number of gates. So then suppose you implement this using this logic expression, you will find out total number of gates required are 1, 2, 3, 4, 5, and 6. When minimized it, total number of gates are required 4. So you are saving 2 logic gates in one module. And when you talk about a system, you are having millions of modules. Millions of modules. So that means you are saving millions of transistors. So that's the advantage of using minimization technique. But problem with K-map is not K-map with Boolean algebra is that you are not always sure whether the way you are going is good or not, or the point at which you are reaching is somehow helping you out or not. So now, when we talk about your Boolean expression, it can be represented in two different forms. So one of them is called sum of products, other is called product of sums. So when you are having this sort of things, so they are called sum of products, and these are called minterms. They are called minterms. I have also discussed in the previous class that suppose f is the function and it is having three variables, then it can be represented as this. So what do you mean by this? It means that for these terms, your output is 1, for rest of them, it is 0. Now, other is called product of sums and also called max terms. So the terms which are left out, 2, 4, and 6, are called max terms. Are called max terms. So if you draw this in term of truth table, so suppose this is your so 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So if you are having it like this, then 1, 3, 5, 7, 1, 0, 1, 3, 5, and 7. The rest of them are zeros. So here you can see it's not working. Yeah. So these, the red ones are minterms. So it can be written as M0, M1, M3, M5, and M7. And the green ones, for which it is 0, are max terms. It can be written as M3, M4, and M6. So other way of writing is M0 plus M1 plus M3 plus M5 plus M7. And this can be written as M2. So this is 2, sorry. This is 2, M2 dot M4 dot M6. So this is the other way in which your sum of products can be represented. So, and this is the another way by which product of sums can be represented. So if you are writing it like this, A, B, C, so it will becomes A bar plus B bar plus C bar and all. So both ways are equally acceptable, but we normally prefer minterms for which output is 1 and we solve it. And the technique which we have discussed till now is your Boolean algebra minimization technique. Now, in the coming slides, we are talking about another aspect that is called canonical form. So, what do you mean by canonical form or standard form? The one which we are actually discussing, like this: AB plus AC is called non-standard form. That means if it is a 3 variable, then C is missing. If it is a 4 variable, then D is missing, and so on. So if we want to represent it in terms of min terms, then it need to be converted into canonical form, or we can say it need to be represented in the form of canonical sum of products. So then things will be better and it's easy to minimize. Otherwise, very difficult to minimize. So suppose this is being given to you that AB plus AC. Now, this is not a standard form and you want to represent it in a standard form. How you are going to do that? In the first literal AB, you will find out C is not there. So you will directly go for C plus C bar. So we already know that C plus C bar is equal to 1. So that means it does not have any impact on the system. So this is the way. Then in this you are having one literal more missing, V. So it will be written as B plus B bar. So in this way, you end up with ABC plus ABC bar plus ABC plus A B bar C. So you will find out from this you are getting ABC, AB bar C, ABC and this. But this term and this term are being repeated. So it is will be taken out of the picture and you end up with ABC plus ABC bar plus A B bar C. So this is the expression you end up with. So this is how you can represent a non-standard form into standard form. Suppose now some of you might be asking that how to convert this into a 4 variable thing. So in 4 variable, it's quite simple. You are supposed to just add D plus D bar here also, because variable D is missing. So it will be D plus D bar and A B bar C D plus D bar. So this is the quite simple thing, and you will make it into a canonical sum of products or standard sum of products. So I hope you get the idea about this, that how you can make your system to standard from non-standard or canonical from non-canonical form. Similarly, if you have a system which need to be converted into sum of canonical sum of products, then how you will do that? So this is the way. So we will discuss this in tutorial. Right now we will be focusing on some other aspects. So here you can see this is your products sums and this is your products. So this is your canonical product of sums. Product of sums. So this is being done like this. So A plus B and A plus B, C is being given. Here you can see C is not there and you will add C like this. Here you will see B is not there and B is like this. So this gives you A plus B plus C and all. A plus B plus C into this. So on. So here this is being repeated, this is repeated. So you are ending up with this particular expression. So That's all as far as this exercise is being concerned. So when we will do this, some more practice questions, and you will be confident enough. So now, suppose I give you a Boolean function in a sum of product forms, and the other form which I have also shown you like this, and I ask you people to minimize it. So how you're going to do that? The first thing is you will go for the truth table. So truth table, you already know. This is the truth table, and you are having the terms A, B, C, and D. This is your output F, and you list them all. So the technique is simple: 0 1 0 1 0 1, then 00 11, then 4 times 0, 4 times 1, then 8 times 0, and 8 times 1. Now we know these mean terms are the points for which your output is 1. For the input combination, for your output is 1. What you do? You list only those like this, and now look forward whether it can be minimized or not. So here you can see this is common. So this gives you A, B, C. Now here D plus D bar is there. This is common. So this gives you A, B, C bar. And here your CD is common. A bar B plus AB bar. And you look forward for other things. If you look at this, clearly it's A bar CD, B plus B bar. So this comes to A bar CD, and this will be taken out. So for simplicity, this is being already done for you, and you will find out that you end up with this particular expression. So here the number of gates required will be more, and here number of gates required will be less. But more often, if you look at this particular technique, so many things are being involved, so much calculations are being involved, and there are grave chances of the fact that you're going to make some errors. So that is not acceptable as far as an implementation is being concerned, that if you are having any error, then your error will leads to number of gates being on the higher side, and your area is in more, and power is more. Also, your circuit may also malfunction if you somehow some algebra is not being there solved properly, then there are always a chances of making some sort of errors. So then people start looking forward for alternative techniques, that how this thing can be get rid of, not get rid of the right word, can be improved, can be optimized, so that we are having at least some confidence that whatever we are doing is right. Then the journey of your K map starts. So that's a K map. So K map is basically a tool for representing Boolean functions of up to 6 variables. Because when things becomes more complex, 4 variable or 5 variable or 6 variable, your conventional Boolean algebra will be very difficult to work with. So this is the definition, and it is somewhere around 1954, I think, or maybe 30s. This is being done by the man Karnaugh. So in K maps, what are having? You are having rows and columns with entries represented ones and zeros of some products and product of some representation. So we will be discussing them in detail. Also, if you are having n variable k map, then it has 2n cells. Suppose you are having it two variables, then you are having four cells. If you are having three variables, you are having eight cells. And if you are having four variables, it is having 16 cells. Then you are having five variables, it is having 32 cells corresponding to a n variable truth table value. Okay. Now, how we have created a K map. How we are actually going to fill the values. So we will fill the values from corresponding truth table, which we are having in possession with. Now, how we are actually going to number them. So K map is being numbered such that adjacent cells corresponds to rows or columns differ by only one bit position. So one bit position means suppose you are having 101, then next number is going to be 100 or 110, because from here to here you can see only this bit is being changing, and from here to here two bits are changing. Okay, so if you are having 100, then its previous can be 110 and its next can be 101. So that means only one bit change is possible. So any one bit can be there, either 110 or this. So if this is your 4, then this will be 6 and this will be 5. Likewise. Okay. So we will be discussing this now. So suppose this is your K map and you want this to be implemented. Okay. So this is for nothing but for your OR gate. We have already discussed this. So you can see this is your OR gate. So before actually going into OR gate, let's discuss its truth table. So its values are A and B. So truth table for OR gate is like this: A, B, and output is Y. So 0, 0, 1, 0, 0, 0, 0, 1, 1, then 1, 0, 1, then 1, 1, 1. So this corresponds to 0, 1, 2, and 3. That's all. Now this is 0, this is 1, this is 0, this is 1. So 0, 0 corresponds to 0, and 0, 1 corresponds to 1. 1, 0, 1, 0 corresponds to 2, and then 1, 1 corresponds to 3. So you will substitute all the values here in this table. So 0, 0 means you are substituting all the values corresponds to the table. So for 0, 0, you are having 0 value. Okay. For 0, 1, you are having the 1. Then for this, you are having value 1. For this, you are having value 1. So you are just filling the value corresponding to truth table in K map. So first thing you are supposed to do is you are supposed to make a K map, and then from truth table you will substitute the values into the truth table. So once you do that, the next thing which is important corresponding to this is mapping. So that we will be discussing in the tomorrow's class. Suppose you are having one more K map like this, A, B, C, and now your variables are sigma m 2, 3, 6, 7. Then you will make a three variable K map. So your three variable K map is like this. Now comes a very interesting thing. So this is your A, this is your B, C, this is your F, and here A will have two values 0, 0, BC will have value 0, 0, 0, 1. Now it cannot be 1, 0. It is going to be 1, 1. as already discussed with you, because at a time only one bit is going to change from 0 1 to 1 0. If this is the change or transition, what happens? Both the bits are changing, and we know that we are using gray code here. So that means only one bit will change. So from 0 1 it will become 1 1, and from 1 1 it will become 1 0. Once again I am repeating this: 0 0, 0 1, and 1 1. Why 1 1? Because if 0 1 to 1 0 transition happens, then this is there, you are having 2-bit change, and that is not desirable. Because of K-map, we have such a thing that we do not want more than 1-bit change. So then it becomes 1 1 and then 1 0. Now you will write the number ABC is 0 0 0 is 0, 0 0 1 is 1, then 0 1 1 is 3, then 2, then 1 0 0 is 4, 5, 6, and 7. I always told my students to take care of this. Whenever they are going to fill this value, the first prerequisite is to number the cells, so that it becomes quite easy to fill the value directly onto the K-map. Otherwise, it is going to be a very difficult thing. You might end up in some wrong information being filled, or it's incorrect information. So now things are being done. K-map is being there. This is being given to you. So these are the values for which your output is 1. So 2, 3, 6, and 7. So rest of them are zeros. So this is how you're going to fill the value from a truth table or Minterm specification onto K-map. In the next class, I'm going to tell you how you're actually going to fill this value into the things, and also we will be discussing how you're going to minimize using this particular technique. So thank you very much. See you in the next class.